As the title implies, this screencast is about RC circuits. R for a resistor and C for a capacitor. And we're talking about a direct current circuit. When we talk about resistors and capacitors in an alternating current circuit, that's a lot more complicated. Now, as we think about a circuit in which a resistor and a capacitor are in series, and then there's a power supply, you'll see that diagram on the next page in just a minute. When the battery is connected and the switch is on, the battery begins to charge the capacitor. Now, normally it might take a fraction of a second to a few seconds to charge up the capacitor, but as you think about the charge leaving the battery full of energy, it's been pumped up by the power supply. You might say it now has oomph, EMF, electromotive force, and the charge begins to head towards the capacitor. When it gets to the capacitor, it encounters the metal plate, and then there's a space before the next metal plate. So the first metal plate begins to accumulate that charge, which makes it harder and harder for the battery to send more and more charge to the metal plate, because now the metal plate is already charged, and of course like charges repel. You can think of this either in terms of the positive charge being accumulating on the metal plate, which is the modern way in which we think about electricity, or you can think about a negative charge as electrons accumulating on that metal plate. And the more you accumulate, the harder it is for more electrons to join them. Eventually, the battery does not have enough oomph to push any more charge onto that metal plate. And at that point, the capacitor is now fully charged, and the current going through the circuit is zero. And again, this might take from a fraction of a second until maybe a few seconds. The equation for this is right here, the charging equation. And so the actual charge, lowercase q, is going to be a function of, or the total charge that's possible, adjusted by this much right here, this quantity right here. Now, just as a sidelight, the letter E is a transcendent constant, much like pi is a transcendent constant. We call them irrational numbers because they go on and on and on and on. However, it's amazing how they fit into a rational universe, which of course was made as a reflection of a perfectly rational God. Creation reflects the Creator. And it's interesting that these are called transcendent numbers, because if something is transcendent, that means it comes from outside of space-time. We like to think as Christians that the laws, God's laws, are transcendent. They're not up for a debate. They're not up for a vote. Human laws are not transcendent. God's laws are. They come from outside of us. So that makes them absolute. That makes them authoritative. The same is true for these constants. Pi and Euler's constant are transcendent, and they show up all the time in various aspects of the study of God's creation. Well, back onto our story. We're going to be using this equation right here in some math problems, and it's also going to be used in a lab 24. So when time is zero and there is no charge on the capacitor, you have your maximum current. When the capacitor is fully charged at some time, and technically it never becomes fully charged because you always have that last electron that needs to travel. We'll talk about that in a minute in terms of time. But as the capacitor charges up, the amount of current in the circuit becomes less and less. So if we look at a diagram of this circuit as well as a graph, if we think of our charge being pumped out the positive side of my battery, and notice the symbol we use for the EMF of the battery, it is measured in volts, but we'll talk about the voltage drop here and we'll talk about the voltage drop there later. And if you add up the voltage drop across the capacitor and the voltage drop through the resistor and whatever minimal voltage is required to get through the wires, that should equal your EMF. EMF, your electromotive force, represented here by the script letter E. So the charge comes over here, it accumulates on this metal plate, which repels an equal charge through the resistor, and eventually, if the switch is closed, it comes back to the negative post of the battery, PTO, plumb tuckered out, 0 voltage. All the voltage is used up in the course of the circuit. If you had nothing in the circuit, we would call that a short circuit. And so you'd have a huge surge of current using up all of its voltage coming back to the battery, and that, of course, can damage the wire and perhaps even the battery. Now, as the circuit is charging up, it charges up very rapidly at first, but then it charges up more and more and more slowly as the capacitor has more and more charge. This is time on the x-axis, and the amount of charge is on the y-axis. So we're going from 0, and we are approaching our total charge Q, If you remember that volts are often defined as my charge, or I should say capacitance is often defined as my charge per volt. And that's where this equation comes from right there. So it asymptotically approaches the maximum possible charge. Now, since we can't know when this line actually comes to this line, and since current is quantized, meaning it has discrete chunks, which of course are electrons, and you can't have part of an electron. You have lots and lots of charges, and then the amount of charge becomes less and less and less and approaches 0. Since we can't talk about the total time to charge it up, we talk about something called the time constant. And the time constant turns out to be that period of time it takes to become almost 2/3 charged of its maximum value. We'll show you where that number comes from in just a minute. So, as I said, it would take an infinite amount of time to fully charge it, because there's always one more electron that could end up there, if you think about the charge as being the electron. But for all intents and purposes, it's in practicality, it is basically fully charged in a finite amount of time for our purposes. Now, the time constant, represented by the Greek letter tau, remember we also used that last semester when we were talking about torque. It's the Greek letter T. Tau is defined as the resistance times the capacitance. And so in order for you to see where this value comes from, I'm going to go back to the original equation. Back to this original equation. I'm going to change colors here for a minute. And if you look at this term right here, when tau equals t, in other words, when the length of time equals tau, and tau is defined as RC, you end up having e to the negative RC over RC, which equals e to the negative 1. And e to the negative 1, come back over here, is this value right there, 0.632. So a capacitor charges very slowly in a circuit that has a big value of tau, and it charges very rapidly when you have a very small value of tau. And typically speaking, after a time equal to 10 taus, 10 time constants, it's basically fully charged. Now, the opposite is true when we're talking about discharging the capacitor. So this is the total possible capacitance, charge that the capacitor can hold. As time goes on during the discharge process, the value of Q, of course, becomes less and less and less. Now, at this point, your textbook says that's how the timing feature works on your windshield wipers. If you have a light rain and the windshield wipers don't need to continually go back and forth, you can put some capacitors in the circuit and they will charge up. And when they get fully charged, they can make the windshield wipers go across the windshield. And then the capacitors have to recharge. We also see that this idea is present in lots of other areas of science, including in biology. It's true in economics. It's going to be true in nuclear. These same ideas are found in all kinds of branches of science. Now, here are those roadway flashers. If you ever come up to a construction site, or maybe there's been a car accident, you might see these flashing lights. And here's how the circuit is designed. When they need to have the flashing lights, they will close the switch. And when the switch is closed, then the charge can be pushed out of the battery, and it's going to go here because through the capacitor and begin to charge up the capacitor. Now you might say, why doesn't it go through here? Well, that's because this is a broken circuit. There's just gas in here, a terrible conductor. There's just gas between the two pink dots. It's not a wire. So the path of least resistance is to go through the capacitor, which charges up the capacitor. Eventually, the voltage doesn't have any more oomph and can't push any more charge onto the capacitor. So now the capacitor is fully charged. Then, when you open up the switch, so I'm going to erase and open up the switch. Now that the switch is open, and I'm going to change colors again. Now that the switch is open, this is the complete part of the circuit. And now all of this charge goes rushing through, and hopefully it has, and if the capacitor is chosen correctly, there's enough charge with enough oomph behind it to be able to bridge this gap, shoot through the gas, and cause it to light up and produce a flash of light. And then, of course, we have to start all over again. So there'll be a device that'll open and close this switch. If we look at a math problem having to do with charging a capacitor, in this particular problem, we'd like to know, for example, find the time constant, and then we want to find what's the maximum charge that we can get onto our capacitor. We also want to do a couple of other things here and find the potential drop across the resistor. And then also we're going to be using Ohm's law to find the current. So how are we going to do this? So coming over to this problem right here. The time constant, of course, is tau times RC. And we just have to plug our values in. That's a piece of cake. No problemo. Next, we have to use Kirchhoff's loop rule. If you haven't watched the video, the screencast on this, or read the chapter, you need to go do that. But Kirchhoff's loop rule basically says through any complete loop, and the loop doesn't have to be round or circular, it can be a square, but through any loop in any complex circuit, the net voltage across and around that loop has to equal 0. So Kirchhoff's law would predict for us that my EMF from the battery, when the charge is pumped out full of energy, some of that energy is going to be used up to charge the capacitor. The rest of the energy has to be used up going through the resistor. And here you might recognize Ohm's law right there, which says V equals IR. And then since you return plumb tuckered out, it must equal 0. That's Kirchhoff's loop rule. And so now we're just going to plug our numbers in here. when my capacitor is fully charged, this value of the voltage goes to 0. And so my, let's see if I said that correctly. I'm going to erase that. When the maximum charge Q is reached, then your current goes to 0. The current goes to 0, and if the current goes to 0, that term goes to 0, which leaves us just this, which is what you see right here. And now we can solve for the charge by plugging our numbers in. Remember, micro is 10 to the minus 6th. Now we can find the charge on the capacitor after 6 seconds. And in order to do that, we need to put 6 in for our time. And down here, that is where my time constant is. And when we solve this equation with my fully charged capacitor, you can see that after 6 seconds, we are about 2/3 of the way, a little more than 2/3 of the way. Now, something else we can do here is try to find out, so what is the voltage? How much of the energy of this charge is used up in charging the capacitor? And so voltage is charge per capacitance because it comes from this equation right here. Capacitance is charge per volt. And again, we're plugging our numbers in. We're plugging that number in. Here's the capacitance in microfarads. And of course, it's negative. Pay attention to the signs because that's the voltage that's used up charging the capacitor. And then finally, when we come down to part D, using Ohm's law, this is my voltage, and this is the value of the resistor, we can find the current. Here's another problem. This time we are going to discharge a capacitor. How long does it take to discharge the capacitor? What's the initial charge and time constant? Some of the things that we want to learn. And so one thing you need to remember is you need to use a different equation for discharge, not the equation for charging. Make sure you know which is which. And we're trying to find 1/4 of the initial value, which means this charge at some time t is Q over 4. And so instead of Q at some time t, remember that does not mean Q times t, Q more as a function of t, I've substituted in 1/4 Q. Notice that my Q's cancel. And now all I have to do is solve for my time factor in terms of tau. So 1.39 tau is how long it's going to take for this to discharge 1/4 of the way. Then we can use the definition of capacitance, charge per volt, to find my charge. Now that we know our charge, we can find the value of my time constant by taking the magnitude of the resistance times the magnitude of the capacitance. And now I have the value of my time constant. And then this last part of the problem, it looks like we're trying to find how long it takes to drain all but the last quantum, remember, chunks of charge. And we've solved it for t, and now we can put my t into the equation here to find my, remember we're going backwards. Instead of Euler's constant E, that's a natural log, and this is the seconds that we get. Last thing I want to talk about just for a couple of minutes is household circuits. Throughout your house, behind the wall board or whatever, you have a pair of wires. And that pair of wires runs from outlet to outlet to outlet in parallel. So even if you don't have something plugged into an outlet, or if something that is plugged into the outlet doesn't work, all the other outlets will still work. You should know that typical voltage fluctuates between 110 and 120 volts. We can use 120 as ordinary voltage in the house. Of course, it's alternating, but we're going to treat it as if it were direct. It's not going to make any difference in the math. Ohm's law applies either way. One of the wires is considered hot, and the other wire is the ground wire, because eventually it's actually physically connected to the ground. In each of your main circuits, there's a circuit breaker, which is designed to flip off if too much current surges through the wire, potentially causing a situation where you could start a house fire. Now, the amount of current in typical circuit breakers is 15 or 20 amps. And the way that works, some work with a bimetallic strip. Two pieces of metal that are different. One metal is going to expand more than the other and therefore act like a switch. And this would be kind of like your bimetallics. And when it starts to bend, it'll turn the circuit off and prevent any more damage. It gets a little more complicated in modern, actually I should have pointed down here. This is one way to do it. There's another way to do it. It's talked about in I think chapter 20. Now, if you do have lines coming into your house and they're not underground, you'll notice that there are 3 lines coming into the house. One is your ground, one is at a positive 120, and one is at a negative 120. So any circuit that is connected here gives you 120. Any circuit that's, if the 2 wires going through the outlets here, that's 120. But if you have your 2 wires coming from the outside, that's a total of 240. And some things that need a lot of current, like an electric dryer, might be 240 volt. But then the greater the voltage, the less the current. So you can still use the same wires you were using before. Now, the last thing you ever want to experience, or one of many things you never want to experience, is to be electrocuted. And to be electrocuted means that the electricity is going to go through you because somehow you've become the path of least resistance. And that can be, for example, if you're standing in water, because impure water is a good conductor. You might remember from chemistry that pure water, only about 2 molecules per every billion actually split up. So pure water is barely conducting. But of course, you're not going to encounter that in a natural setting. So electric shock can be fatal. It can also give terrible burns. But the damage that is done depends on 3 things. How big is the current I? How long is this current going through you or some part of your body? And of course, what part of your body? For example, you don't want it to go through your heart. And in one of the handouts in this chapter and in the very introductory screencast, I talk about these different current values. Some will give you mild shocks, like 5 milliamps. Twice that amount will cause your muscles to contract. If you grab hold of a live wire, you might not be able to let go because your muscles will contract. And you're going to need somebody to knock you off. You don't want somebody to grab you and pull you off because then they become part of the circuit and they become, their muscles lock as well. That's not good. Then when you get up to about 100 milliamps, that can be fatal. And interestingly enough, 1,000 milliamps or 1 amp might not be fatal, but it can do some serious burns. Now, modern appliances almost always have a third wire. Sometimes it looks like this, or sometimes you can see it in an outlet. It just looks like this in an outlet. This one would probably be for 240. This one would be for 120. But this extra outlet right there actually ends up going to the ground. That's the symbol for going to the ground. And it would be a wire that would run through the walls, probably all the way back to the circuit breaker, and then connect to a pipe or a really, really thick wire, thicker than, let's say, your thumb, that would go down into the ground. And then that becomes the path of least resistance, and that saves the current from going through you. In the meantime, when it goes back, it's probably going to trip the circuit breaker, and that opens up the circuit breaker, opens up the circuit, and now nothing will work on that circuit until you fix the situation, which you should do, unplug some things, and then go back and trip the circuit breaker back on again. Maybe you've heard of a ground fault interrupter. A ground fault interrupter is a way of if your piece of equipment, in this case an electric drill, is getting old and there's a frayed wire, maybe it's been dropped and it's rattling inside. If the electricity were to touch the case, the electricity is going to go through you. That's not good. You hate it when that happens. But if you've got that third wire is going to take it back to the ground. And that's called, that's a safety mechanism. A lot of your outlets also have a ground fault interrupter. I was looking to see where that was. A GFI. The ground fault interrupter is often around sinks in the kitchen, in the bathroom, wherever there might be water, or maybe even outside, so that if there is water in the area and there is a short, instead of going through the water in the area and potentially through you, it'll take the path of least resistance, which is that nice, hefty, good conducting copper wire, and take it back into the ground.